So we have, and I forget what textbook I got this. I think it was the old Larson textbook, but it was entitled, so you see here, three similar integrals. And you look at what you have here, and they all look very, very similar to one another. Right? Subtle differences. Denominator's the same in each case. The numerator gets more elaborate as you go on. But there is an underlying structure to it. Now, if you can kind of get a sense of what that structure is, then you're going to be in good shape. But you're not really going to be able to do much unless you have a pretty good grasp on some of the rules, because sometimes just looking at something, you know, if you have a sense of the rules, it speaks volumes, you know. So you may look at number one and immediately see that as a rule, right? That is, let me just make sure, because I keep doing that. That is the arctan of x plus c. All right, and that's by definition. I'm not 100% sure why I left, like, I don't know, 15 lines of space between this one and the next one, but that's it. That's a rule. That's knowledge. All right, somewhere along the lines, let me just see. Yeah, on the next page, I have all those rules in there for you. So I just typed it all up. I put it in its most general form, but this is focusing on this particular rule here, just in terms of x. All right, so if I were to take the derivative of the arctangent of x, I would get 1 over 1 plus x squared times the derivative of x, but the derivative of x is equal to 1. So that would bear itself out. All right, sometimes it's that simple. And if you look at the breakdown of what's going to be on the test, the first question is going to be just basic integrals, so rule-based questions. So if you know the rule, or if you have access to the rule, then those become very easy. All right, but sometimes, and I've mentioned this before, if you don't know enough to look at your note card, then it's kind of like, yeah, all right, I wrote it on the note card, but I'm not familiar with it enough to know that it's worth it to look at the note card at this moment. Then what's the point of even having it on the note card? So don't just blindly put something on your note card. Have a good reason, have a good sense of the material, and just put it down there as your safety net. All right, now the second one. It's triage. It's that first nurse you talk to when you go to the hospital. They figure out what's going on, and then they send you in the right direction, right? So the first thing we look for is a rule. The second thing we look for is some kind of U-substitution, all right? So can I define a U such that the derivative of the U would cancel out the other part of the integrand? In this case, it's a fraction, but we would take the more complicated part, x squared plus 1, differentiate it, du equals 2x dx. And if that gets the job done, then you need not look further, basically. Right? You don't have to go looking for a really complicated way of solving these things, because the very last thing that we covered, the partial fraction decomposition, that was, I think, the most complicated thing and had the most moving parts. I don't think that you want to lead off with that. You want to kind of end the journey with that, right? And so this could be the way you handle that, right? So 2x dx, I'm highlighting the wrong thing. 2x dx is the same as du. So now I can do a switcherooski here and replace the 2x dx with a du, and replace the u with an x, the x squared plus 1 with a u. Some people like it in this form better, 1 over u du. Which is ln of whatever that u is plus c. and the u is x squared plus 1. Now in this case, I wouldn't need the absolute value brackets. You could just use regular parentheses if you want, but you can never go wrong if you put the absolutes in there. I mean, you'll never be wrong if you put the absolutes in there. So make that your default. The reason I say you wouldn't necessarily need it in this case is because if I take a number, square it, it's positive. Add anything to it, it's just going to become more positive. The only thing with logs of any kind, natural or otherwise, would be that you can't take the log of a negative number, you can't take the log of 0. Right? So here I'm looking at something that works out to be non-negative anyway. So if I forgot and didn't put the absolute value brackets, it would be okay. So from your perspective on a test, let's say you just whip and forget you accidentally put parentheses instead of brackets, absolute brackets, you got away with one because it turned out that you didn't need them anyway. But if it were x squared minus 1, you do need them. And you would be wrong if you did not have the absolute value brackets there. So what do I say? Just put them in anyway. Play it safe. All right? So the second thing you're on the lookout for, aside from a rule, first thing is the rule. The second thing is, can you define a u? All right, first thing is to try to find a rule that fits, even if it's something you have to slightly modify. Maybe, the first example wasn't 1 over x squared plus 1, maybe it was 2 over x squared plus 1. All right, that's very close to being the rule, except you pull that 2 out, and now it's a rule. So it's a slight variation away from being a rule. Or maybe part of it's a rule, and the other part is just simple reverse power rule or something like that. Like for example, if I had 1 over x squared plus 1, and then separately plus 2. You could look at the first part as your rule, and the second part you would just do the reverse power rule. Okay? Still a rule, but of a different variety. Okay? One where you actually have to do something. All right? The third type of situation here. Now this is where things get dicey, because there isn't a direct rule that we can apply, an inverse trig rule. There isn't a u that we can define, because if I call this u, its derivative would still be 2x dx. That's not canceling out the top. All right, so now we're kind of in a jam. But there are ways out of the jam, because we learned a technique last class called partial fraction decomposition that could help us. But there's also another way that you can go about doing it, and it goes back to pre-calc. You could just try to divide the top by the bottom. All right? So when would you know to use partial fractions versus some other technique? If the bottom of the fraction is factorable, then you want to start thinking in the realm of partial fractions, because what that would generally mean is that two things were added together. You had to get a common denominator. Two separate fractions. You had to get a common denominator and put it together. Here, I don't know, what would we be looking at? It seems like it already has a common denominator. Now, we can try partial fraction decomposition. Sometimes it ends up just being more trouble than it's worth. But then also, sometimes it's exactly what the doctor ordered. I'll try it this way, and then I'll show you the nifty little trick that might make your life a little easier. All right, so it's up to you as to whether or not you want to write this down. But if you want to refer back, because we didn't really tackle much when it came to quadratics last class for partial fractions. We're looking at something like this. So if your factor in the denominator is something along these lines, then your numerator is going to be a linear, I'll call it a linear factor, but it'll be a linear expression. All right, so the expression that goes in the top of your fraction is always going to be 1 degree less, a function that's 1 degree less than what you have on the bottom. So linear goes to constant, quadratic goes to linear. If I had cubic, it would go to quadratic, and those are nightmarish. if that's the kind of thing that you're interested in. But you might say, all right, I'll give it a whirl. So look at this again. And I would say, all right, well, I got my denominator, my quadratic denominator, and then my numerator would be some sort of linear expression, ax plus b. So right off the bat here, you're in a pickle, because it looks like it's not going to play out, but we can try. So we factor. Let me do it this way, so I only write it once. X squared plus 1. Because it's the kind of thing that just doesn't feel like it's going to work. So at that point, you might say, the hell with it, I'll try something else. So you look at this expression and you say, all right, now what? Because I need to equate terms that have x squareds in them together from left to right, and terms that have x's together left to right. It's a mess. It's not going to work. Right? So we tried it. It failed. So let's try something else. And I'll tell you, this little clever technique that I'm about to show you, it's so cool. I did not come up with it. Because when I come up with stuff, I'm like, I say things like, "Oh, this is a pretty good approach. You might consider using it." Because I don't want to say that this is an awesome technique if I came up with it. Because if you say no, it isn't. It sucks. We hate it. Then I'm like, oh, I came up with that one. And then, now you hurt my feelings. So this one was other people came up with it, but when I saw it, it like blew my mind as, whoa, we can do this. It's incredible. I often pride myself on the fact that I can understand everybody else's work. Like reading a math textbook, work online, everything. I can make sense of it all, and I'm proud of myself. I don't always come up with the stuff on my own, though, right? And this is one of them. But after I saw it, I thought to myself, maybe I should have. All right, so I'm going to add 1 just to the top. Now you look at that and say, well, how can you do that? Like that's not possible. Like you're making stuff up now. So if I had something like 2/3, I can't just add 1 to it, because now it's 3/3, and 3/3 is not the same as 2/3. So I'm going to subtract a 1 from it. Now it's of equivalent value, right? 2/3 is still 2/3, yeah? So this is legal. So why can't we do it with an algebraic expression? All right. So then you look at that and say, okay, cool, we're with you. Now why the hell did you do that? What was the purpose? Before, I wasn't able to split up the fraction because there were no pluses and minuses in the top. But now I can. I can split it right in here. Make 2 separate fractions. X squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. So x squared plus 1 over x squared plus 1 becomes a 1. The other guy would just leave as is. And this is kind of what I was alluding to in number 1, where if you have, it could be a rule-based question with a little extra something in it. This, I don't need a rule for. I just use normal integration techniques, reverse power rules. This one is a rule. So I could take the antiderivative of those separately. So the antiderivative of 1 becomes x, and so minus. Then the antiderivative of that's just the arctangent of x. plus C. So if your thought was, hey, I never would have thought to do that, cool, you're just like me. So for better or for worse, it means you're just as smart as I am. That it would be natural log if this were something involving an x on top. Okay. But you bring up a good point, because I could look at this, I could write this as plus negative 1 over x squared plus 1, and write this as x plus arc cotangent of x. So the idea that there could be multiple answers to the same question, that is fair game. All right, and so you may have looked at something like this and come up with a different answer. It could be equally as valid as mine, which is why you want to do things like using your calculator to check your work, especially if you come up with something pretty elaborate, because, you know, there's often times where you look at your answer and say, all right, no way that's right. And then the calculator tells you, well, actually it is. It's just really ugly. Or you come up with something you think is a beautiful solution, and your calculator says, yeah, it looks great, but not everything that looks great is good. So now, how did I know to do that? Aside from the fact that I just exposed you to a new technique, right? So that's a big question. Our relationship is the key, right? So if you're looking at something that is almost a rule, specifically an inverse trig rule, but the powers are the same top and bottom, then this technique could come into play. But I'll show you in a minute how it can be used in other cases also. But it's that power relationship that allows the whole thing to work. It just basically, can I manipulate the top in such a way that part of it will be the same thing as the bottom? If the answer is yes, then that's a good method to use. It was a false start. It was an idea of like, I'm putting myself in your shoes. What's something that might cross my mind? I might look at it and say, let me give partial fractions a shot. Give it a shot, it doesn't work. Instead of saying, all right, that's my omit, try something else, you know? So this would be the third strategy. Take a look at those powers. If they're the same, then that means that there's a strong chance that you can manipulate the top to at least have part of it be the same as the bottom, which will then allow you to break up the fraction and then allow you possibly to do something from it. Okay. With fractions, it really comes down to those three strategies, or it's a crapshoot. So if those three things don't work, then it's like, all right, well, I tried those three things. Now you kind of go down your list. What comes next after that? The dreaded trig substitution. I'd say dreaded, not because, well, personally, I don't think it's overly difficult to perform. It's just involved. You know, it's just one of those things, like, you know you're in for a page of work, so you don't want to lead with that. So when you go through the other three possibilities and they don't work out, that's when you have that sinking feeling of like, all right, I just got to do the page of work, and I'm just not happy about it. It'll get done. You'll get the answer. It's just like, it's root canal. You know, it's got to be done. It's not the most terrible experience in the world, but you just got to sit through it, you know, and find a spot on the ceiling and just stare at it for the next 45 minutes to an hour, you know.